So good morning. Thanks all for waking up for these lectures today. I myself was having too much fun doing machine learning last night, so I probably stayed up a little bit too late. In fact, I'm still doing the calculation on my computer right now, which is why the laptop is open. And hopefully by the end of this lecture, my machine learning optimization for a particular fun problem will be done, and I can analyze the results during Nathaniel's lecture. Uh, so today, what we're going to do is we're going to be talking about putting some of the things that we learned yesterday into action in the context of the simulation-based inference of trying to figure out the structure of the universe by comparing simulated data to real experimental data. And maybe I didn't say this clearly, but the thing that we did last time in terms of the kind of mechanics of machine learning is we learned this thing called the likelihood ratio trick. This is a trick for extracting ratios of probability densities. And it turns out that that's basically all we need in order to build an engine to do simulation-based inference. So just to remind you where we were last time I said that the ingredients for machine learning were having trustable training data. Maybe I forgot to say the word trustable. If you have garbage data, then you're obviously not going to learn something useful. You needed to have some objective that you're trying to optimize. And I gave you a homework assignment, which we'll mention in a bit, about trying to show how that objective behaves. And just to say that this is very closely related to Lagrangian mechanics. And because of that fact, we as physicists are in a good position to come up with new types of loss functions because we can just think about how it would behave if it were a dynamical system. We talked a little bit about strategies for learnable functions. Most people focus on this. They focus on the neural network part of machine learning, but neural networks are just one particular way of parameterizing functions. And there's many different strategies. And for the optimization that's happening on my laptop right now, I am definitely not using neural networks. I'm using my physics domain knowledge to come up with an alternate functional forms. And yet I'm still doing the other parts of this pipeline. And then finally, an optimization algorithm, some algorithm that could rocket you down from some arbitrary starting point, rocket you down to the minimum of some function, which turns out to be a hard problem in general. And one of the challenges of machine learning is that when you're doing this optimization, you can get stuck in local minima, or you can get kind of off in some weird sidetrack. And that's one of the kind of arts of doing machine learning, is figuring out optimization algorithms that are appropriately adjusted for the loss that you're trying to minimize. But I just want to emphasize this point again. You have control over what machine learning is trying to accomplish, at least in the asymptotic limit. You can understand what it's trying to do. It is not a black box in that sense. Sometimes the results that you get are confusing, but this pipeline is one that you have to establish, and you have to think about your science goals to figure out whether the problem that you set up is really the right one for what you want to do scientifically. Okay, and so then I gave you a homework that I'm curious if anyone actually tried to do this exercise. Okay, we have 0. That's fine. So one of the things that I realized is that my handwritten notes have not been uploaded anywhere publicly. And so maybe this is something I could work with the organizers to figure out how to get my notes into the hands of the students.
Sure.
The
sounds my
Yeah. But the thing that I said that might be fun for you to do is to take two samples drawn from P and Q, building the loss function that is basically saying, for sample P, I have a particular loss term that's some function A. For sample Q, I have some particular loss function that's this function B. And different choices of A and B correspond to different machine learning loss functions that are in the literature. And the one that I derived for you was this thing called the maximum likelihood classifier loss, which is a mouthful. But we argued that kind of a maximum likelihood approach should be giving you logs of this function W that I'm trying to learn. And then I made a mistake. I forgot this one. Someone pointed this out afterwards, that I wasn't properly normalizing my distribution. Remember, this term was a Lagrange multiplier that helped impose a constraint that the learned distribution was normalized. So there's a 1 that corresponds to the constraint that it's normalized to 1. Yesterday, now recorded for posterity, it has 0, and certainly probability distribution should not be normalized to 0. Anyway, you put this 1 in, we have a 1 minus W term, and we then argued that the minimum of this loss function is achieved functionally if W is fully flexible with this ratio P over Q. And then the minimum itself has this correspondence to a statistical measure, the KL divergence. And more generally, different choices of A and B, good choices of A and B give you something that's related to P over Q, and then some statistical measure that you can use to assess similarity. And this general trick for different choices of A and B, such that doing this learning dynamics will at least asymptotically give you this ratio. This is called the likelihood ratio trick. So these are objects that, okay, this is really density ratio trick. I'll turn it into likelihoods in a second. But this density ratio trick or likelihood ratio trick, this is a kind of a workhorse of machine learning that we'll take advantage of for this lecture today. Okay, so are there any questions about that before we jump into taking this machine learning stuff and injecting it into an inference pipeline? Okay, so what's the big deal? um, we've known about the importance of likelihoods and likelihood ratios since forever, certainly since before machine learning. I mean, normally what you would do is you would construct likelihoods and like actually try to analytically write them down or estimate them using some kind of histograms. So what's the big deal? Why did I spend a whole lecture on this? Um, and the answer at some level statistically is there's no big deal. We've known that this ratio is important. So I used the symbol W in the lecture last time because W was a weight that we were using, but let me change the symbols into being a ratio, R, and let me abstract it. Instead of saying it's specifically phase space, let's say any type of data, ratio R, P over Q, and we've known since forever that this is important. The thing that's new, the thing that machine learning allows you to do, and I'm not really going to explain how this is possible. It's kind of a miracle. There's actually some kind of interesting stat mechy ways of thinking about this. And this would be a fun thing to discuss maybe more during Q&A. It happens to be that despite the fact that in general, learning is a complicated process, apparently with machine learning strategies like the ones we discussed last time, this X can be super high dimensional. As I'll say a little bit later, normally what we would do is make it low dimensional, turn things into histograms, compress our information. But apparently, machine learning is very happy for X to be super high dimensional, and that's the reason why it can process giant corpuses of text or images and videos or sound. And this is a little bit of a surprise, and the fact that it works so well, again, it's be fun to discuss, but there's a little bit like kind of a stack mechy understanding behind it. That's kind of normally you'd say in a high dimensional space, how could you possibly explore that whole space? But StatMech gives you an example of being able to, despite the fact that we have huge dimensionality of phase space, for example, for all the positions of the molecules of air in this room, and nevertheless, we can make generic thermodynamic type statements and we actually get fairly robust behaviors. And something like that is going on in the context of machine learning. So X can be high dimensional, and moreover, this R can be actually quite flexible, such that it can be flexible enough to model the complexities of this ratio. Again, I'm not really going to explain why that's the case, but that's also part of the engine uh, of um, of of, uh, of behind machine learning. So I'm going to try to explain how I can turn this ratio, this likelihood ratio trick, a strategy to extract this ratio. I'm going to assume that I'm going to be able to do this, and I want to turn this into the simulation-based inference pipeline. And I've drawn this a number of times, but it's fun to draw it again, where we have some underlying theoretical model, let's say, of the data. We have the experimental data that I see. I'm able to do faithful simulations of what that data could look like, and then I want to infer what the fundamental parameters are. It turns out that this is basically all you need. Once you have this framework is not so difficult. Okay, so that's where we're going. But what I realized in preparing these lectures is that I can show you that it's super fast, one board and I can do it. But actually, there's more core confusion that people have, and including myself have. Um, about statistics, and we're not trained oftentimes very well in statistics. Especially as theoretical physicists, our experimental colleagues often have more experience with these things and are more expert. But as theorists, oftentimes we kind of, I don't know, we maybe use statistics in a more cookbooky way. And I want to try to dive a little bit into just some of the philosophy behind statistics, because it turns out that philosophical aspects kind of explains why this tension between the way machine learning is kind of set up, which is quite Bayesian in nature, versus the way that we're going to want to deploy it. We're going to want to do it in a frequentist way, and these things are a little bit incompatible philosophically. And again, we're going to be able to we will succeed, but it helps maybe to talk a little bit about what that philosophical distinction is. So I am not a statistics expert myself, but that's probably a good thing for your learning, since I'm probably just as confused as you are. And I've been trying to wrestle with these things, and in wrestling with these things and putting these notes together, hopefully I've run across similar confusions that you already have. I'll do my best to try to explain them. So my first confusion is a really basic one. What is probability? Um, like when we talk about probability, what are we really referring to? And we really need to understand the definition at some level of what probability is, because this is tied to our notions of uncertainty, our notions of being confident. When I say the words 5 sigma, what does that mean in terms of some notion of probability? And the cartoon version of the two main paradigms of thinking about probability um, are frequentist and Bayesian. Um, and the distinction between frequentist and Bayesian, uh, frequentist says that probability is frequency of outcomes. Um, for under exact replication. So we're imagining, for example, the ability to, if I'm doing cosmology, to start with the initial conditions of the universe and like exactly reproduce the process of the universe evolving. Or maybe we imagine even having fluctuations, the initial conditions of the universe, but the distribution over those fluctuations is something that is known, reproducible. Um, we have exact replication. For a Bayesian, probability is different. So probability is a degree of belief in the underlying theory. And so this is more like casino odds, like saying, "Hey, I'm willing to bet you $20 that something's going to happen, or 20 euros." And probability is whether you think you're actually going to, on average, gain money by your beliefs. Um, and both of these philosophies have flaws. Um, so for a frequentist, probability is frequency of outcomes under exact replication. Sure, if I'm a collider physicist, I can more or less reliably generate arbitrary amounts of data over and over and over and over and over again. Just exact replication, exact replication, exact replication, and I'm not starved for data. And really, when we're doing things, we can do that exact replication. But in cosmology, I really can't restart the universe, and so I can't really make repeated measurements. Okay. The flip side, Bayesians, which is the more cosmology way of thinking, is this probability of degree of belief in the underlying theory. And as we'll say, that requires human judgment in a way that can make you feel uncomfortable. We would like to think that scientific decisions are ones that are immune from our humanity, or foibles of humanity. But really, they're directly connected. And in fact, at some level, Bayesianism is more correct in the sense of it's really the probability that people usually think about when they think about, there's a 95% chance of it's going to rain tomorrow, or there's a 95% chance that I've discovered a particle. That's probably more correct, because that really is partly related to human judgment, but it requires choices that can make us feel uncomfortable. Um, But maybe just to say, and we're going to see in a second that machine learning actually has elements of both in a second. But if you want a kind of slogan for frequentist versus Bayesian, a kind of slogan for frequentist is that the data is variable and the probability is associated with that variability of the data. The different types of outcomes I could get for the same theory, that's the thing that probability is capturing. But the model is fundamentally fixed. Of course, we don't know which model it is, so there's a choice of which model might explain our universe, but we just imagine that if I were God, I would know that fixed model. So the data is variable, and the variability, that's what's associated with probability. Whereas Bayesianism is the kind of the other way around, again, in cartoon form. Here you would say that the data is fixed in the sense of, you only have one universe. You can't restart the universe. You have one data set. You can't get more information. That's it. The data is fixed, but the model is variable, which is to say that the notion of probability is associated with your degree of belief that that model is the correct one that describes the universe. And I guess sometimes since both of these are wrong in the sense that in reality, our data is fixed. We only get to do our experiment once. Yes, I say in collider physics that I can collect arbitrary more data, but it costs more and more money. So for a fixed amount of money, I really only have one data set. And I would like to believe that the underlying theory of the universe is not stochastic. Maybe people would like to disagree with that, but I would like to believe that the underlying theory of our universe is fixed, like at some fundamental level, that it doesn't carry any sort of variability to it. That's actually kind of an interesting quantum field theory question to ask. But in some sense, this is the truth. And yet, we can imagine doing multiple experiments. We can imagine the data being variable. And we can imagine with some probability that different models are correct. And so this part is also correct. They're all correct. Why? And what's the complication? Well, what's probability? Probability is involves things that don't happen, right? When you place a bet on a football match, one team's going to win and the other team's going to lose. There's a fixed truth, and yet we have a probability betting odds associated with the outcomes. But because probability is associated with things that don't happen, in addition, of course, to things that do, it's understandable that there's different schools of thought about what probability is.
So in matter of statistics, if I had infinite data, do I get different outcomes? Even if I assume that no knowledge is like flat liar.
Well, right. So you said you said the word flat prior. It turns out that even that, right, starts to introduce biasing effects. I mean, it is true that these two philosophies end up giving you very similar answers in practice when you have enough data. But actually, there's like a meta question, which is, well, what was the model you're going to use for the first place? And as you're collecting more data, we typically get greedy and build more and more complicated models. And I think the experience of humans is that we're not satisfied with one fixed model. As the data starts coming in and the error bars get smaller and Bayesian and frequentists start to agree, then we get aggressive and say, ooh, let me check this other thing. Let me check this other thing. The models grow. And in practice, you end up back in the same situation. So, like right now, we now have the data to ask questions about the time evolution of dark energy. And we have reliable data to now say that question. So now you've expanded model space, and now you need priors over that model space. And because we are greedy as scientists, greedy for knowledge, it ends up being that these distinctions still end up mattering, even in the case of quotes infinite data, because we may just make the models more complicated. So in preparing these lectures, I decided that I should probably actually understand more about probability. Because you hear about these two pillars of statistical thinking, Bayesian versus frequentist. But it turns out that there's more than just that, and there's all sorts of different notions of what people think about probability being. And this will not enter into our science discussion today, but it's actually kind of entertaining to see other philosophies of probability. Um, and seeing how they relate to things that we're familiar with in physics. So one philosophy is probability as just counting options. So there's this joke that the chances that the Large Hadron Collider are going to destroy the world were going to be 50-50 because either it's going to happen or it's not. Right? So that's just counting options. Probability is counting options, and we can laugh at it, but there's an area of physics where counting options is the basis for what we do in physics. Anyone want to stat mech? Stat mech entropy. All we're doing is we're counting options that are, of course, we have to decide what we mean by distinguishable versus indistinguishable. But in stat mech, our notion of probability is all things that are possible or with equal probability. That's what we do in stat mech. So that's a philosophy of probability that then gets manifested in the way that we talk about thermodynamic quantities. There's probability as a physical attribute. So when I have a particle and I say this particle has a branching ratio to these various final states, we're asserting that, let's say a muon, a muon has an intrinsic property that it wants to decay with some probability to electrons and some number of neutrinos. So when we're doing that, where we're assigning probability like a physical attribute, that's basically what we're doing when we're doing quantum mechanics. We're basically saying like something like the wave function of a state or the branching ratios or scattering amplitudes of some configuration. We're really saying it's kind of intrinsic to that object that we're studying, or intrinsic to the wave function. That is, even if I don't make a measurement, there's still somehow a notion that that you have a well-defined wave function or well-defined amplitude. So there's another thing that you can think about probability as some kind of logical framework, like trying to assign values of truth. Is it true or false? And broadening that out to saying, well, it's true that or false with kind of some probability, and using some kind of logical framework to generalize the notions of ands and ors and other logical statements. And then there's probability as kind of a pragmatic tool. And that's what we're doing when we're doing Monte Carlo integration. We're sampling. So that's a notion of probability with the probability of a phase space point. But we don't usually think of as doing any sort of deep philosophy there. Like Monte Carlo integration is a numerical tool that's using stochasticity as a resource. So as I said, because probability involves things that don't happen, it's maybe understandable that we have all these different types of notions of what probability could be. Particle physics tends to be more on the frequentist end of the spectrum. Cosmology ends up being more on the Bayesian end of the spectrum, but it's worthwhile understanding these different frameworks more generally. And as we'll see, they're basically tied together by once you have the likelihood ratio, like then you can decide what you want to do with that information. And so that's the reason why both Bayesian and frequentism appear in a machine learning context. I actually see advantages of all these different approaches for thinking about probability. You just have to be sure that you know what you're doing. And kind of ultimately, at the end of the day, we're making decisions. We're making decisions about whether I'm going to put a fact or not into a textbook. Am I going to make a claim of a discovery? Am I going to award someone a Nobel Prize? In some sense, all these notions of probability feed into a broader kind of decision theory about how we make scientific decisions given incomplete information. Okay, any questions, objections, additions, comments? So the key assumption of simulation-based inference is that you have access to the following information: access to a joint probability, And in this case, I really mean joint probability in the more pragmatic sense. Like someone gives me a bucket of data, and now I need to process that data, and I'm going to process it as if it were draws for a probability distribution. So we haven't necessarily assigned a philosophical meaning to this yet. And let's see, what notation am I going to use? Okay, I'll just use the notation in my notes. So I keep switching between x and phi and other things. So let me just use what's in my notes, which is x. Joint probability, the probability of x. So x is my experimental data or theoretical data, comma theta, which is the parameters of some model. So I'll in a moment remind you about ways of manipulating probability, since not all of you do this on a day-to-day basis. So we have access to this joint probability, the probability of the data and the probability of the model. That is, the data is variable and the model is variable. But the limitation that I have is only through samples, that I only have samples of this data. I have draws coming from this probability distribution, but I don't actually have the analytic form of that object directly. So at some level, we both have frequentist information, frequentist style variability. I fix the model and I can ask what my data could look like given that same model. But also Bayesian information, that is, I had to choose how likely a given model is for whether I include it or not in my training data set. And now, given this thing that kind of has multiple notions of probability, we now need to squeeze this into a form that I can use for either Bayesian or frequentist inference. Okay, so there's some very basic probability that I want to make sure that we know. And I've already been using this notation, but uh, uh, let's remind ourselves about it. So if I want to know the probability of x and theta, well, what I can do is I can first draw a value of theta, the probability of some model. And then I can say, given that model, what's the probability of getting that value of x? So what's the probability of me getting that data given a model? Then I multiply by the probability of the model itself, and that gives me the joint probability. But nothing stops me from reversing the role of x and theta. So I can also say, first what I do is I say, pick me the data. Then, conditioned on whatever data I see, select the model. And the equality of these two sides, this is just like almost definitionally, rearranging this gives the famous Bayes theorem. But at some level, Bayes theorem is just kind of a basic, almost like definitional of what we mean by probability. So part of the challenge with statistics is that unless you stare at enough of these things, they all look quite similar. Um, and then also, uh, if you really want to drive people crazy, um, I think that the standard notion for the likelihood of of uh uh so which way is the likelihood of a model given data is equal to the probability of the data given the model, or something like that. And so I just don't want to even think about like different notation. If we're going to stick with just this one notation, okay, and yeah. So maybe they use semicolons. I forget, but we're going to try to avoid proliferation of notation and only manipulate things that look of this form. This is the thing that's variable. The first thing is variable, and the second one is fixed. And rearranging this gives you Bayes' theorem. And Bayes' theorem says that the probability of theta given x is equal to the probability of x given theta times p of theta divided by p of x. And these all have names. And again, all the symbols kind of look similar, but they have names, and it's helpful to try to keep them separated in your brain. So this thing is known as the posterior. This thing, the probability of x given theta, that's known as the likelihood. this P of theta is known as the prior, and this P of X is has a confusing name in my opinion. This is called the evidence. I don't actually like that name, but um and but again, these are just names that we assign, words that we assign to these symbols that just come from basically if you have a two-dimensional distribution, you want to slice it and dice it in different ways. The different ways of slicing it just have different names. And then just as another kind of fact that we can talk about, so this is called the joint probability. We also have marginal probabilities. And marginal probabilities just come from saying I only care about the probability of either the data or the model, but not both. And what we can do is we can just integrate over the thing that don't care about. So if I take my joint probability distribution for x and theta, and if I integrate over theta, just integrate over theta, then theta goes away and I'm left with a probability for x. And same thing the other way around. And so, as you're manipulating these expressions, there's multiple correct ways of expressing some of these quantities. And our goal at the end of the day will be taking likelihood ratios, which are not appearing anywhere in what I've discussed thus far, and turn that into a frequentist inference engine. And so Bayesian logic has to do with this posterior. That's not the object that I want to do for frequentist inference. Frequentist inference will be focusing more on the likelihood directly without extra decoration from this prior. And that's the thing we're going to have to figure out how to deal with. But again, the key assumption is that I start off with this joint probability. I start off with all this information, and then I need to manipulate it in a way to isolate the thing that I care about from my particular statistical technique. Okay, so let me pause here and see if there's any questions before I try to explain to you why machine learning is kind of intrinsically, if you'd like, Bayesian. Yeah.
Is the maintenance here always build up your body get the data, or is just that I have to base on the two is basically first?
Right. So let me repeat the question. So the question is posterior always the probability of the model given data, or could I just replace this with A and B and scramble it up? And do not do that, otherwise a Bayesian will strangle you. Because remember, in the definition of probability, data and models are treated asymmetrically. So the way to read Bayes' theorem is I start off with a prior. I start off with a probability that I think a model is correct. That's my prior knowledge. The posterior, post meaning after, is, well, after I've collected some data, I'm now going to update my belief, update my probability. And the way that I update my belief in the model is through this structure. So the order matters essentially for this. Of course, at the end of the day, it's just a 2D probability distribution. So if I have, and the fact that like what they have different philosophical is like whatever. It's just samples drawn from some multidimensional distribution. But when you're doing inference, it really matters what order you go in. Yeah.
But can we get the same law? Like you just get like the sharp poke is a lost robot and get like the like posterior or they take as the model.
Yeah, you can manipulate it that way, but then again you'll have like the whole stats community strangling you. Yes, and so at the end of the day, when you say I'm doing a statistical procedure, there's also like the philosophy behind that statistical procedure. None of this, by the way, is God given to you. This is our way of deciding how we want to process incomplete variable information. And as I mentioned, StatMech processes probabilities differently. Quantum mechanics kind of thinks about probabilities differently. In fact, a lot of the debates about the underpinnings of quantum mechanics, they come back down to just a basic question about what is probability. Okay, even just classical probability. But the fact that you're seeing that these things are manipulable in this way, that's a feature, not a bug. It's a feature because it will allow us to use machine learning to actually extract a lot of these quantities. Because machine learning is kind of agnostic as to the inference pipeline. Okay, so machine learning wants to be Bayesian. And this goes back to a joke that I was I think on the first day was making about a colleague that I was talking to, who was kind of claiming that they didn't want that they were doing a fancy machine learning regression problem, and they weren't just learning some kind of mean of a distribution. And let me show you that example. But now with the symbols corresponding to model and data, like we have on the board now. So we're just going to do symbol regression again. So I'm doing the identical thing that I did on Monday. I'm just changing the symbols. So I have a loss function where I now imagine sampling from both data and model. And what I want to do is I want to find a function that inputs data and spits out what the model is. That's what I'm going to do. This is classic regression. And this is kind of what you think about with machine learning. Machine learning is trying to say, I ingest information, then I want to make a decision. Ingest information, make a decision. Good decisions are when this loss is 0. That is when your decisions mimic the training data. Okay, so we can do our Euler-Lagrange again, vary with respect to f, set it equal to 0. And I won't go through the algebra again, but when the dust settles using this notation, you'll find that f of x is equal to, so you vary with respect to f. F only depends on x, so the integral over theta remains. And then it's p of x comma theta divided by p of x, where the p of x, if you want to do this at home, comes from applying the theta integral in that definition of the marginal. Or by using the definitions of all these various objects, this is the same thing as having the integral d of theta of p of theta given x times theta. This thing here is the posterior. This thing here tells me that I'm calculating the mean. So what regression is doing when using these symbols is just finding the average over the posterior of your model parameters. If that's what you want, great. This is how to get it. So posterior is your probability, your degree of belief in your model, given the data that you're seeing. You're not certain, you have a spread in your degrees of your beliefs, and you take the average over those different parameters that corresponds to. That's the thing that you report. Totally fine. Mean of the posterior. But the mean of the posterior, by the equation up there, explicitly depends on the prior. So this is what I mean by saying that machine learning is kind of intrinsically Bayesian, that is intrinsically prior dependent. And this is also what people worry about with AI training data being biased. That theta is like the prior over selecting people who are older versus younger, and that there might be biases according to age or some other personal characteristic. And that's coming from the fact that your training data has baked into it kind of underlying probability distribution over the model. And that's one way that AI biases can come in if you're doing things in terms of regression. Yeah.
Where's the expert data in the setting?
Well, it comes from me not writing it on the first line. Thank you for correcting me. So that for all posterity, we have the correct theta, unlike that stupid normalization of the probability that will haunt me. I won't be able to sleep tonight, both because I have a super exciting machine learning thing, and because I know that forever I will be on video saying stupid things. But I guess we have 7.5 hours of me saying stupid things on video, so that's fine. Okay, so any questions about this? Machine learning is intrinsically Bayesian. Based on this. But so then you might say, well, wait a second. Aren't we always going to be prior dependent? After all, your input here, your joint probability distribution, it depends on the prior. How could you possibly get away from the prior dependence? Isn't it always true that you can only do Bayesian inference with machine learning? How could you possibly do frequentist inference? How could you possibly make the prior go away? How can you possibly get rid of biases? Okay, so sometimes these biases are good things. That's another way of saying what a prior is doing, is it's biasing your decision in a direction corresponding to information that you already have. If that information is reliable, that's a good thing. If it's not reliable, that's what we worry about. But doesn't it seem like it's always dependent on the prior? And the answer is no. And I will show you the way. But because it's so simple, I'm going to postpone it for another 15 minutes. Okay. So it's really easy, but I don't know. This is the building of suspense. Because otherwise it's hard to justify the rest of this lecture. Because once I show you the answer, you're going to say, "Oh, that's easy." So I need to keep you in suspense, and so I'm going to use this as an excuse to give you some more statistics. Okay. Any questions though before I go on? Okay. So the thing that I want to explain to you, and I apologize, is to explain to you Bayesian versus frequentist inference at the simplest level that I know how to do it. As I said, I'm a kind of a statistics novice. So I know I've oversimplified things. So I'm enough of an expert novice to know that I'm not telling you everything. So that's maybe a good sign. But let me try to do kind of basic frequentist versus Bayesian inference. So let's start with basic Bayesian inference. So basic Bayesian inference, if someone hands you P of X given theta, and maybe I should have said this, but emphasize it, is that if I have the joint probability distribution of P of X comma theta, I can generate any of those objects using these equations on the board. So in particular, I can generate the posterior. So this, the posterior, after having seen data, what is my degree of belief in theta? So the posterior is a probability distribution over theta. And you can define, there's various things you can do with this object, but you can define credible intervals via quantiles. So P of X, theta given X, that's a real probability distribution over theta. Again, to a Bayesian, the data is fixed. There's one data set, don't get to collect anymore. Given that one data set, you have a probability distribution over theta. Looks something like that, let's say. And then if you want to know what's your uncertainty or your credible interval over theta, what do? You slice off, let's say, the middle 95%. There's many different strategies that you could do. And this is 95% of models are in this range. And then you report that. Or you report some other things. There's many different objects that you can report. When you see a Bayesian talk about 95%, they really mean given a probability distribution over the parameter, there's a 95% chance that that parameter lies in that given range. Of course, it's prior dependent. And if you choose a stupid prior, you're going to get a stupid posterior. But it's easy to interpret. Because, because it's directly a probability. So in some sense, anytime you really are talking about probability, you're probably talking about it in a Bayesian sense. You're imagining, the probability that when I say that I have a confidence interval on the mass of the Higgs boson, you probably say, well, yeah, 95% chance that the Higgs boson mass is in this range, or 95% chance that the cosmological constant has a certain value. That's probably what intuitively we mean by probability. And that's Bayesian inference, and I can get it on one slide. Sadly, frequentist inference is much more complicated. And frequentist inference, there's all sorts of language around it, but it's based on the opposite object. So it's based on the likelihood, P of X given theta. And this is an object that if you're simulating the universe is very natural. I input the parameters of my simulation, out pops the data. So when you're running a Monte Carlo event generator, you're setting the values of physical parameters, seeing the data that comes out. This likelihood is the kind of natural thing that you're generating. And again, here the model is fixed. I set my Pythia settings and then I go. I don't need to specify a prior over the Pythia settings. So that object is the likelihood. To make this have nicer dimensions, we usually divide this by some reference model. And this thing is a likelihood ratio. Likelihood of some variable model parameter divided by likelihood for some fixed reference value. So this is a likelihood ratio or likelihood ratio tests. So this object here is the likelihood ratio. And the thing that's confusing about the notation that I'm using, this is very standard notation. This is the likelihood ratio of theta. It's the thing that's missing, which is it's x dependent. This depends on the data. But standard notation leaves that fact out, or when they do put it in there, they put it in with a condition this way, which is like the flipped way around, and that makes it even more confusing. So I don't know whether I should carry a little subscript X on this thing, but remember, it's data dependent. This thing here is not more underlines, even more underlines, not a probability over theta. There is no direct probabilistic interpretation of this object. It's just a thing, a ratio of functions. This thing is probabilistic. The likelihood is the probability of me seeing different types of data, given my model. This ratio itself, not a probability. And yet, what we're going to see in a moment, that we're going to kind of interpret it kind of like that for reasons I'll explain. Let me just see if there's any questions. Thus far, Plato, yeah. Yeah.
We had snowball or some other.
Yes. But I don't see how I don't know how he continuously plays them in some interval there.
Ah, good. So here I'm imagining theta being a continuous parameter. But you can easily treat the case of discrete. And so the easiest way to make this plot, if you want to have discrete data, is you just say, so are you imagining just two outcomes, or?
Yeah, uses it more.
Okay, so let's say we have two outcomes. So we have the probability of model 1 given x and the probability of model 2 given x. And so if this is 83% and this thing is 17%, there you go. I've done everything for you. So the only reason, that's the full information. The only reason why I'm making this plot here is that if I have a continuous variable, then do I really want to report the probability density for each slice? No, I want to summarize it into one number. So when I say I have a 95% credible interval, that's assuming that my parameter is continuous. If it's discrete, you just list the answers. Is that?
Yeah, well, I know. Maybe that will be but the wrong way. Let's say we use GR. This will be 48 per case. The of measuring some category law. This some exclusive 83 versus 7%. Am I movie?
No, it really does. Like the example you just said is, what's the probability that I observe the perihelion precession of Mercury under Newton's laws versus to the accuracy that I measured experimentally compared to I should say, what's the probability of seeing the measured data, including all of the complications of the measurement apparatus, whether it's a cloudy night when you're trying to make your measurement, what's the probability under all those assumptions of seeing a certain phenomena given Newton versus gravity? And it really does come in this form. So that's a perfect example. So what we typically do is we typically try to generalize our hypotheses in such a way that it isn't so binary. So, for example, in particle physics, you will often use what is mu called? The signal strength. So instead of saying the standard model is 1, and I want to know, is it 1 versus 0? I'll say, well, no, let me generalize the standard model to have a variable signal strength and then put a confidence interval on the signal strength. But you could just do a binary test, standard model with Higgs boson, standard model without Higgs boson, because one of them violates unitarity. So big prior belief, my prior would be that I need a Higgs boson. So that's oftentimes why you introduce parameters to make sure that as you're varying over parameters, you don't get something pathological. So that's why we want to infer the Higgs boson mass rather than doing that binary comparison. But like, I would say at some fundamental level, what you're raising is the reason why, or is like the core thing that we need to do when we're doing experimental design, is we have to say, what are the hypotheses that we're testing? And can we write this thing down? Like, okay, can I write the likelihood down? Can I say, I have an awesome model of quantum gravity? Can I say, what is the actual data that I would get from my awesome model compared to the data that I would get from some other hypothesis? And if I can't write down that likelihood, then I don't know how to do inference. I can't make a judgment about whether the data favors one versus the other. Does that answer your question? Yeah. Okay. So there are two different types of things that people do. So there's p-values, which is a kind of a notion of probability with respect to the null hypothesis. So p-values we choose for the reference some fixed theta naught, which is called the null hypothesis. And so there we imagine a space of models. So the example of signal strength is a good one, where I could like say my base assumption is saying that the standard model is correct, but then I want to know maybe the signal strength can be varied. For parameter estimation, what we typically do is we choose the reference that we use as the thing that maximizes the likelihood for the observed data that I see. Okay, so what I do is I take this object, the reference is fixed. So when I optimize over theta, the denominator doesn't matter, and I choose the maximum likelihood estimator of that theta as the thing that maximizes this object. That's called the MLE. But the MLE itself, let me decorate it with a little X here. It's data dependent. So different data that you see will give you different values of the maximum likelihood estimator. So even if you have the same underlying model, the thing that you estimate for that will change. So, if I do LHC run 2, I get one estimate of the Higgs boson mass. LHC run 3, I'll get a different estimate of the maximum likelihood Higgs boson mass. Each data set has a different reference point. But again, this is a standard thing to do. And then we want to interpret those reference points, these reference points, these MLEs, we're going to manipulate those to then turn that into not just a point estimate, but give me an uncertainty bound. So this thing, this is so painfully confusing. Data is variable. Therefore, anything derived from the data is also variable. Therefore, the maximum likelihood estimator of your parameter itself varies depending on the data that you see, conditioned on the true value. I have a true model, but experiments are not perfect, and therefore I get different distribution, or sorry, different values, a distribution of values for the maximum likelihood estimate. So this is the true value. Again, to a frequentist, models are fixed. And this is now my variable estimate that if I took my data over and over and over again, that's what it would look like. And this, under reasonable assumptions, kind of with these squiggles are doing a lot of work here. These things are approximately Gaussian distributed. So these things are approximately distributed around the true value with some uncertainty. Again, these squiggles are doing a lot of work here. And I could say blah, 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 Wilks theorem, blah, blah, blah. but that roughly speaking, you can kind of think in most cases that you're going to encounter that the things are roughly going to look like this. And if you want to work harder to get the distribution more accurately, you should just do that hard work. And there's various statistical strategies to do that hard work, but that's enough for the purposes of this lecture. So as a parentheses, more accurately, just to say the words you might hear, but more accurately, the test statistic that's defined by minus twice the log of this likelihood ratio follows a chi-square distribution to a good approximation, at least follow a chi-square distribution asymptotically. And all a chi-square distribution is a kind of a fancy way of talking about it follows the distribution that you would expect from a Gaussian random variable. This is a dramatic oversimplification. My apologies to the statistics experts who might be watching this video. But the point I want to emphasize is that this MLE, that's variable, even though the model is fixed. Okay? Okay. So, what then is a confidence interval? And these are the things that are reported when, at least in the frequentist context, when someone says I have an error bar on some parameter, they're reporting this confidence interval. What it is not triple, quadruple, whatever underlined, some kind of quantile, not a quantile range. It's not like the Bayesian case. What it is the following. Okay. So on the so I think I did this the right way that it's in the literature. Apologies if I've transposed my x and y axes. And now I have this moment of distrust whether I'm doing it the standard way or exactly the flipped way. Okay, so anyway. So on the y-axis is going to be the true value of the model. This is the fixed thing that's God-given. This is fixed. This is being plotted versus the range of, for example, in this case, we're going to, more generally, it's the range of test statistics, but in this case, it's just the range, let's say, of maximum likelihood estimate values. More generally, it's the test statistic. Okay, and these things are variable. So for a fixed true value, I can come up with a 95%, let's say, interval on the range of MLE values that I'll see. And if I run enough simulations of the universe, for this value, I'm going to see some range. For this value, I'm going to see some range. For this value, I'm going to see some range. And hopefully, if your MLE is reasonable, then the relationship between the MLE and the truth should more or less follow like a diagonal line. It never does, right? So you have to correct for biases that come from this procedure. But roughly speaking, MLE should be a good proxy for the truth. But remember, truth is fixed. I get probabilities this way. And I can take these things and I can turn them into a probability belt. Oh, maybe I can use colored chalk here. So I can turn these into a probability belt. That's not a good colored chalk. That's only slightly better. I'm giving up. I'll have to figure out the chalk situation for tomorrow when I'll actually need it. So I'm making this into a band. Remember that there's an asymmetry between the y and the x-axis. There's a probability this way, no probability this way. And yet we're going to want to put a probability that way. And so what you do is you say, I have observed my MLE value. I have my experimental data. So boom, this is the experimental data that I have. So this is the value of the MLE that I get from my experiment. And then what do? I then say that my confidence interval, so this is 95% of experimental outcomes, and then I turn that into a confidence interval on my true value. This is the naming construction. This is how you can convert probabilities on experimental outcomes, how you can convert them into probabilities on true parameters. This direction is actually a probability. This one is some weirdo projection, and this is the standard in our field, at least for collider physics. Gussied up with turning this into real test statistics and such. Does that make sense, roughly? So what we say is that assuming that the universe has a certain true value, then the confidence interval, that's the thing that varies. Like to a Bayesian, the model itself is the thing that varies. For us, like the confidence interval varies. And then 95% of the time, your confidence interval will actually overlap with the true value for a given true value. So it's a weirdo notion of probability, but that's the price you have to pay if you want to avoid prior dependence. Okay, now it happens to be that if things are approximately Gaussian, you can, roughly speaking, interchange the role of theta MLE versus theta of the model. And so when you do this projection, you can kind of reverse the notion of what's probabilistic and what's not and get away with it. In general, that's not true. But we will do this cheat. And so at the end of the day, when some reports, for example, n sigma confidence intervals, what they'll say is that the true model parameter lies in the range of the MLE estimator minus some estimator of the variance, MLE estimator plus n times the estimator of the variance, and then the estimator of the variance you get by, okay, this is now kind of asymptotically, and there are all sorts of corrections, yada yada, but you take the second derivative of the logarithm of that lambda with respect to your parameter. This is the one parameter. You can generalize it to more than one parameter. You take this thing, you take the inverse evaluated at the MLE. So just to narrate this thing, so we already said the MLE basically, if there's no bias, the center here turns into the center there. The range here depends on how wide this Gaussian is, and then the width of that Gaussian I can extract by taking this function, taking two derivatives with respect to theta. Two comes down, and then that gives me 1 over sigma squared, and then I take the inverse, and that gives me the variance. And that is the calculation that's being run on my laptop for for not one parameter, but oh god, it's a lot of parameters that it's working on right now. Okay, but these formulas are a bit deceptive. It looks like theta is a Gaussian variable. The thing that's Gaussian variable is the estimator of theta, not theta directly. Confusing? Yes. Frequentist logic can make your brain hurt. That's the price of avoiding the prior. No prior dependence. We stand on our head. But now I don't have to worry about the biases coming from the fact that I had to choose the distribution over models. Okay, any questions before I summarize and then show you the actual trick? Yeah.
Then was created to get the bad. So we just assume Amalacida quantita, and given the data we example, we get the rate of the filter as
Yeah, so let's say mechanically what we're going to do. Mechanically what we're going to do is we're going to let's do the Higgs boson mass. So I have my Monte Carlo event generator. I set the Higgs boson mass at some value, fix it at one value, generate some data. That gives me 1 MLE. And I do my whole analysis plate line. That gives me 1 value of MLE. Same setting, generated again, another value, another value, another value, another value, another value, another value, another value. I then make the 95% central region, or quantile, here. Okay, new value of the Higgs boson mass. Same thing. I generate all sorts of random data. Each time I get a new value of the MLE, boom, I get my interval. I then take the edges of those intervals, I connect them together, that gives me a band, and then I do my procedure. Super computationally intensive if you want to do it correctly. Without machine learning. With machine learning, it'll be really relatively straightforward, because what machine learning basically will say is that you'll sample over your data, you'll sample over the values here, and it'll make a nice interpolating thing that then I can use to build this band more computationally efficiently. Does that make sense? Yeah.
The number 95% that you get is for the right?
Yeah.
How do you
the percentage of the quantile is the reported percentage when we say we have the confidence interval. So when I say I have a 68% confidence interval, what I did is I did the quantile on the MLE, or more generally a test statistic, and then I used that to find the edges. So if I did I kept saying 95% for this, so 68 would be smaller, and therefore the band would be smaller. And in the Gaussian limit, it scales just like this for n sigma confidence intervals. Does that make sense? Okay, so let's see. I guess I'm gonna erase everything. But let me. So again, what do we need for this? We needed this thing in the box. We needed the likelihood. And then once we have that likelihood, then you just have to trust me, or having followed these lectures or following better lectures by people who do real statistics, that all of this procedure that we went through is just dressing on top of that object, and that's the thing that we need. I feel a lot more calm now that we erased all the Bayesian logic. Okay, so if you have that object, then there is a frequentist machinery to turn it into confidence intervals on theta. And the amazing thing is that your machine learning training data will depend on the prior. It depends on that joint probability. That doesn't care. How are we going to get it to cancel out? And the other thing that I want to say is statistics is really subtle, but oftentimes we take that as an opportunity to be saying, oh, it's subtle and it's hard and I'm going to ignore it. View it the other way. That means that there's opportunities for innovation. And especially in an era where we're asking deeper and harder questions, statistical innovations, it's not just, arbitrary data manipulations. It really is the way that we understand how our universe functions. So it's worthwhile thinking about those statistical aspects. Okay, so at long last, the trick. I want this object. I have the ability to generate ratios, and again, I can't agree on my notation, but ratios with training data of P of theta, Q of theta. And you say, well, these don't look the same. Like, first of all, the symbols are different. But then also, this has P and Q. That's just P. Like, what's going on? Okay. So, I don't know. It's like too simple. I'm afraid of writing it down. So let's replace theta with actually two variables. Phi rather, with two variables x and theta. So just with the change of notation, I can imagine having a joint distribution over x and theta and a different joint distribution q over x and theta. And with that likelihood, sorry, so with the likelihood here, I'm allowed to normalize that likelihood. So again, this is what I want, but now I'll be slightly modified. As long as, when I'm doing my inference, as long as I put something in that doesn't care about theta, it won't change the maximum likelihood estimator. So that annoyingly called thing that we had called the evidence, I'll just decide to put it in there because that's something that I can build that is theta independent. So all I've done is I've taken the thing that I want and just normalized it by some way that's irrelevant. So this is my choice. Okay, I want this thing. Can I get it? Well, let's just write the definition of it. So P of x of theta over P of x P of theta. That's just expanding the given part. So this is the given. I could just unpack that. And then apparently I'm supposed to identify that with P of X given theta and then Q of X comma theta. Which means that somehow I'm supposed to have in my denominator distribution Q of X comma theta is just P of X P of theta. So the numerator here is clear. We said that that was the ingredient. That was my joint distribution of data and models. My denominator here is apparently supposed to be the product of the probability over data separately and the probability over model separately. Oh, but that's really easy. I just compute the marginals. And in practice, what you do is you just take your data set where X and Y are paired, X and theta are paired, and you just randomize them. And so you just like pretend like they're unpaired. You just like drop it on the floor and reshuffle. And that's a way of sampling from this. And we're done. So that was clearly too fast. But let me see if there's questions. And then I'll re-narrate what I just said. So the thing that frequentist inference wants is it wants probability of X given theta. I can arbitrarily normalize it. Doesn't change anything. What machine learning gives me by doing binary classification between two different samples, I can compute the ratio. A particularly interesting ratio is the joint probability jointly of data and model divided by the product of the marginals. That's also something that's very easy to generate machine learning training data for. I just undo the correlation in my data set. One data set is correlated, the other one is uncorrelated. I train those things off each other using, for example, the loss that I showed you, the maximum likelihood classifier loss, and we're done. And moreover, I mentioned before yesterday that machine learning losses are related to statistical quantities. And I said in particular that if I use this maximum likelihood classifier loss, the result is this KL divergence, which is very famous in statistics. If I replace KL just by putting in the definition of Q, and I say, what's the value of the loss minimum? So I'm just plugging in the things that he had before. The value of the loss minimum is dx d theta, probability of x and theta, times the logarithm of P of X comma theta divided by the product of the marginals, P of X and P of theta separately. Does anyone know what this quantity is? Have you seen this before? I'm curious. You may not have.
This is like the mutual.
Yes, it is literally the mutual information. Mutual information. And this makes like incredible intuitive sense. We're trying to do inference. We're trying to say, given data, I want to infer model parameters. Mutual information tells you if you have information of a given type, how much does that tell you about the other thing? So mutual information is a measure of the degree to which one information about one variable tells you about the other. So this is saying if I do collect data, how much do I expect to learn about the universe? How much do I expect to learn about the model? And the difficulty, so which way does it go? If the, if the mutual information is 0, then one doesn't tell you anything about the other. But that means that the loss is very small. So the difficulty of getting to a small loss, the difficulty for a machine learning algorithm to get a small loss in this particular task, that's actually the degree to which the data that you collect actually tells you something about the universe. Incredibly satisfying. And that's another reason why I like this particular maximum likelihood classifier loss is that it has a beautiful statistical meaning. And so that when I'm doing my inference, not only do I get my frequentist yada yada, but I also get this like information theoretic concept, a number that tells me kind of how much do I think I'm going to succeed in the business of understanding our universe. Good? Okay. So from here, there's many different directions that I can go. And I'm debating in myself which way to go. So the things that I'm definitely not going to do, I'm definitely not going to talk about network architectures that can make this procedure to make SBI easier. But that's a fun topic to explore. There's other applications of this same trick, other applications of this likelihood ratio trick that go beyond inference. I'm not going to do that. There are alternatives to the likelihood ratio trick, that there's other strategies for inference that don't use this particular machinery. So this I will definitely not do. But in the remaining time for this lecture, there are two topics that I'm debating which one is better to do. One is about incorporating uncertainties on the machine learning itself. And the other one is about the capability that this unlocks, the capability of unbinned analyses. Both of these are near and dear to my heart since I've written papers about them. But in the interest of time, I'm just going to do one or the other. I have a default in my brain of which one I wrote in my notes first. But let's see if there's a strong preference between these two things. So just by show of hands, and you don't have to raise your hand if you don't care. Who would like to hear about incorporating uncertainties? Okay. Who would like to hear about capabilities of unbinned analyses? Yeah, it's less so. So sorry. Happy to talk about this. Let me say that this idea of frequentist inference and whatnot, if you read about it, a lot of it has to do with doing binned analyses or doing things with histograms. And doing things with histograms is limiting because you have to choose the histogram parameters. With this framework, you can actually do full unbinned analyses, and these have actually been done already. And there are results coming from various experiments where you use the same machine learning trick with a very high dimensional space, and you're able to report the outcomes of an analysis, again, using this trick in a way that has good statistical meaning. Okay. So, okay, we're going to do uncertainties, or a way of doing uncertainties. And I'll come back to this point on Friday. Not the uncertainty part, but the thing I'm going to say next. And this has to do with a lot of different strategies that people are doing for processing data. And to a first approximation, the only thing I know how to do is parameter estimation. On models. We just did this whole frequentist inference thing, super statistically rigorous. That's the only thing I know how to do. And there's no real such thing as a direct measurement. Even this kind of capability of unbinned analyses, we're talking about like doing full phase space measurements. Like at some basic level, and if I had time, I would do this in notes. At some basic level, it's still an inference problem. It just happens to be it's an inference of parameters over models that are pretty complicated, but it's still an inference problem. So, when you say I'm going to measure the Higgs mass, can I do that? Well, what I'm really doing is I'm inferring the value of the Higgs mass given some model of P of whatever my data is given the Higgs mass. When I'm measuring some Dijkstra's cross-section, am I measuring the Dijkstra's cross-section? No, I have some model of if I were to have a cross-section, what would that look like in my data set? Am I measuring the cosmological constant? Am I measuring the expansion rate of the universe? No, you have a simulation that has a parameter in those, and you're inferring the values of those parameters from the data that you're seeing. You might say that this seems kind of limiting. But it's really, really not. Why? Because machine learning, and more particular neural networks or its neural network-ish things, are very flexible models. Okay, so you can do the following. You can infer, okay, what is the probability of me seeing the LHC data set given some rando neural network with, I don't know, 1 trillion parameters. And then you can do frequentist inference to figure out the maximum likelihood estimate of all the neural network parameters, as well as the covariance of those things. And that trillion by trillion parameter model, like that gives you the probability distribution of seeing the LHC data given that model. You can do it. Now, would you learn any physics from doing that? Right? I could train a generative model with all these, and I can do this procedure, but would you learn any science from it? No, typically we would like to have uh, uh, physics-based understanding physics-based models. So now you're in you swung the other direction. Neural networks are so flexible that if you could do this trillion by trillion dimensional correlation structure, you really could infer something, but that inference wouldn't have physics meaning. And so we have these kind of like two different extremes. One extreme is the extreme of kind of physics only analyses. Physics only analyses are limited by your ability to really do reliable simulations. And then we have, let's say, machine learning only models, which is limited by any notion of physical interpretability. And one way of thinking about incorporating uncertainties in the machine learning itself is, can we find a happy medium ground here where we really are going to be relying on reliable simulations, but combining them with neural networks in a way, but still have the ability to compute error bars and uncertainties and things like that. And that's what I'm going to show you one way of doing it, certainly not the only one. So let me just pause here if the philosophy is clear. Like, if you say that I want to model the universe, you can model it with something stupid. You could literally have a model that says, I'm going to give you a picture for every single time place of what things look like. That's a highly variable model, many, many, many parameters. I can just like mimic by taking a video recording and let's say, well, that's my model of what I'm going to see is literally just what I saw. That's not a very good model. It's not an explanatory model, but you can do it. And we would like to find a happy medium between these extremes. Okay. So so more generally, we're talking about uncertainties or or uncertainty quantification, which is a kind of vast field. And just like there's different philosophies of probability, there's different definitions of what you mean by uncertainties. In physics, you'll encounter statistical uncertainties versus systematic uncertainties, but even those words don't really capture the richness of what uncertainty can encompass. This is a vast topic that's underexplored. I mentioned innovations on the statistics end. A particular innovation on understanding better uncertainty quantification would be very, very welcome. But let me only use the ingredients from this lecture to talk about a particular approach for uncertainty quantification. And if I take the strict frequentist worldview, that knowledge has to be encoded into a likelihood. And in particular, I need to know the probability of my data given underlying model parameters. If I'm a little bit more sophisticated, I might put in nuisance parameters. So these are the model parameters that I care about. I might be a little bit more sophisticated and put in nuisance parameters. And then, so with just this, I can, do MLE, and I can figure out, the confidence intervals on theta and nu. But if I'm doing this in a machine learning pipeline, also in principle, I have to account for the probability of the data, given the models, given the nuisance parameters, and given, for example, how I'm setting up my neural network. But to the extent to which your neural network is just defined by some more parameters, I could also do confidence intervals on theta, nu, and the neural network parameters. Why not? And that's basically the philosophy we're going to take. Now, I should say that this thing in general is really hard, even if I don't put this neural network thing. Like, this is a hard problem. As I mentioned before, these are very high dimensional spaces, but this is what we have to do to encode our knowledge. We have to come up with models. This is a different, there's like model building in the BSM community. This is like a very explicit version of model building where but now you're really saying, what's the probability of all sorts of possibilities of the data given some model assumptions and nuisance parameters? This is the thing that we have to do. And then there's the statistical pipeline in order to actually get the error bars on that. And I would, at some level, argue that this is what we have to do when we're doing curiosity-driven fundamental physics research.
So probably depend on the neural network. So that if let's say we had the neural network to learn, probably.
Yeah, exactly.
Why is that?
Because so the probability itself is, of course, some kind of meta object. But what we're really doing is we're really coming up with an estimate for the probability distribution. And the estimate for the probability distribution is dependent on the neural network parameters or other choices that you've made in your analysis. So you're right that there's like this kind of meta notion. That's what I was doing before, kind of asymptotically, this meta notion that I have this probability, but I don't have direct access to it. I only have samples from it from a simulation. And then it's only as good as my approximations. And that's why it's sensitive to the neural network parameters. But it's really funny, right? And ignore the fact that I did this as a neural network. Just say whatever assumptions that you made in doing your analysis. And if you encode those in continuous parameters, then you can do the same thing here. And ideally, in a perfect case, you would vary those assumptions that you made. They wouldn't matter and you'd be done. This is just like the limiting case that if you have enough data, the prior doesn't matter. But in practice, you cannot assume that the neural network has found the global minimum. You can't even assume that the neural network has converged. So it will give you an estimate for the probability, but it's going to be completely wrong in general. In fact, this research started for me thinking about uncertainty quantification from an experience that I had with a student where the student was so proud of what they'd done over the summer. And I asked to see the results, and they were very impressive results. And then I started looking at the code, and what the student had actually accidentally done is copy for the final results the answer from an untrained neural network. It just happened to be that an untrained neural network was really good at solving this problem. They'd done lines and lines and lines of code and then undid it by just loading in the original model and not the final model. And it's like, well, how would I have known that would happen? Like, how would I know to check? And so, no, I told this story to various people saying, oh, Jesse, you can check in this way, this way, this way. It's like, yeah, but what if those checks come out being okay? Because this student convinced themselves for like a whole summer project that they were doing something sensible. And the reason why is that neural networks are amazing, like objects out of the box. But how would you gain confidence in it? And what tests would you do? And so they said, oh, you can do this test, this test. And it's like, no. I want to have confidence in the frequentist confidence interval sense, which is why I'm proposing this here. But am I answering your question about why you kind of need to do it? Yeah. But a lot of times people ignore the uncertainties associated with the use of machine learning directly. Okay. So here is the proposal. So here I'm talking about experimental data, but let's say even like earlier on in the pipeline, we're not doing real experimental data. all I want to know is what's the probability of Monte Carlo data, given my model parameters, and given the way that I'm using to estimate the Monte Carlo data, the procedure that I use to build an interpolating function, if you'd like, that interpolates over the Monte Carlo data. Now, if this is 1 trillion parameters, or even 1,000 parameters, then getting the confidence intervals and all the correlations is super painful. And my laptop has not exploded on fire, so that's a good sign. But it's basically trying to compute something like that, like that object, and it is churning away. But what we can do the following. That is pretty reasonable. So here's a trick that works reasonably well. That is, you can, after the fact, check whether on test cases, whether it did what you wanted it to do. So what you do is the following. You say, I'm going to model. So this is now really modeling or meta modeling. This is like a meta model. I'm going to model. It turns out for technical reasons, it's better to work in log space. I'm going to model the logarithm of the probability distribution of my data. In this case, it's Monte Carlo data, given whatever parameters in my theory are. And I'm going to start by modeling it with a neural network. So I have some neural network, and this neural network, okay, I'm giving it the same symbols over here. So it's like the probability of x given theta and the nuisance parameter. So I'm writing it this, but remember, this is just a function. So I've succeeded in modeling this thing as a function. More specifically, you're modeling this ratio to some reference. Okay, so I do this. I do it once. I get an answer. If you're a bad machine learning practitioner, you would do it once and write your paper. In fact, if you're a really bad machine learning practitioner, you do it I times, and you choose the best performing out of the I based on whatever arbitrary measure you've decided. Submit only the best answer to NeurIPS and get the glory, even though 999 times didn't work, but that one time it did work. You report only that. So this is the machine learning version of p-value hacking. So let's not do that. But typically you are training multiple neural networks, multiple approximations to the likelihood. So let's take those multiple approximations to the likelihood and treat them as if they were a real physical manifestation of the likelihood. That is, we're going to have a model that will depend on weights that I assign to my various neural network possibilities, summed over all those possibilities. And then I'm going to do frequentist inference on those weights, along with theta and nu. Okay, that's what we're going to do. So this is with my current student, Sean Benavides. This thing appears in versions of this appear in the literature under other names. We call this Wi-Fi ensembles, just because you have weights and neural networks F, so Wi-Fi. And so if you want to think about this kind of colloquially, we worry about AI hallucinations. So you have a bunch of AI hallucinations. As an aside, I'm trying to coin a new collective noun. So in English, you have collective nouns like a murder of crows. So I think the collective noun for AI chatbots should be a hallucination of chatbots. So I have a hallucination of chatbots. I weight them in some linear way, at least linear log space, take their sum, and then treat this as if this were the model itself. Now, this thing has names, as I said, in the literature. This is, if you look at, for statistics, this is related to, they call it exponential forms or exponential models. Various types of this weighting have appeared before. The standard thing that's done in the machine learning literature is to take these weights. If I have k models, take the weights as being 1 over k. So just to get equal weight. So, you have the chatbot that is completely wrong and the chatbot that's mostly right, but you give them equal weight. Like it's a democracy, everyone has a vote. Okay. But no, we're smarter. We can do frequentist inference. And so instead of having to give everyone the same weight, nope. What we can do instead is I can tell you what the MLE estimator is. That is the thing that is best model of the data given that particular functional form. So I'm making an assumption. I'm making an assumption that my data is in log space, a linear combination of these neural networks. But now it changes completely the way you think about neural networks. Now neural networks are not trying to get the right answer out of the box. Neural networks are trying to get an ensemble or a spread of information such that a linear combination of them is accurate. So you cannot trust one hallucinating AI chatbot, but a hallucination of AI chatbots appropriately weighted satisfies the requirements of frequentist inference. And then, of course, you can complain about this functional form. But now we can argue at the level of, do you believe this functional form? But at least the statistical uncertainty quantification inference side was completely well defined by what I've already said in the lecture. Was there a question? Now, okay, at the end of the day, it's a bit more involved than what I'm showing here. And I learned a lot of statistics along the way of doing this project with Sean. But I think it's a kind of just another example of how you should be thinking about machine learning as just a resource that takes sample data and converts it into objects, optimization in response to data, gives you these objects, and then you can manipulate and study those objects in the way that makes sense to you. And this particular approach of manipulating them, after I've done training the neural network, the rest is effectively almost like linear regression problem, a more classical stats problem, which makes me feel warm and fuzzy and able to sleep at night. Okay. So, let me see. Are there any questions before we adjourn? Okay, we need to get coffee. So let me just kind of summarize these last two lectures. So hopefully I've given you some insights into inference, both Bayesian and frequentist, in the context of machine learning. Basically, machine learning plus trustable simulations allow us to do this pipeline. And while I could spend the next two lectures talking more about that pipeline and going into more detail, I think you basically have enough to, at least for inference problems, kind of look at what's in the literature and be able to at least start to scrutinize. What I want to do for the next two lectures is I want to step away from standard techniques in particle physics and talk about alien technology, or also technology from French mathematics of the late 1700s, which was alien to me, and give you an example of a branch of machine learning that has been really influential in my research. It happens to be also Nathaniel has worked on this topic, and it's an emerging area. It's a hammer in search of a nail. I find it really beautiful. We've done some fun things about it. I talked about it at the public lecture on Monday, but I want to use that as an example of how learning from other disciplines of science might give you insights about how you might approach your physics problems. And then on Friday, we'll just idly speculate for an hour and a half. But this is what you had in these last two lectures, kind of the core of the information that I wanted to give you as part of these GGI lectures, give you a sense of how you do machine learning and how you apply it to statistical inference. And then we're going to have more fun, at least more fun from my perspective, during the rest of the week. Any last questions before we go for coffee? Okay, thanks very much.